go. So we were talking about this thing called the scientific method. And if I could ask to everybody, make sure your mic is muted because I'm hearing some snaps, crackles, and pops. And I don't think it's my breakfast. Actually, you might have seen this in the news that Snap, Crackle, and Pop have been murdered. The police are saying it's a serial killer. Right. Okay. So we were talking about how the science thing is done. And I talked about how it starts with a hypothesis. Yes, thank you. Very funny. A statement of how some aspect of the world might work, and the hypothesis has to be put to some sort of test. Very often that's a formal experiment, and we'll talk about how experiments are done. There are fields of science where it's just not possible to test hypotheses by experiment. Astronomy, this happens a lot. Some aspects of medical science, it would be unethical to do experiments. So we just do our best with observations that we make. Some hypotheses are tested by building models, either math models or in some cases, computer models, more and more often computer models. Ultimately, you have to either support your hypothesis or reject it. Now, if it's supported, you still have more work to do because there's always a chance that the test wasn't a good one, that you'll find some other way to test your hypothesis and it will fall down. Any hypothesis always has to be open to further testing. If your hypothesis is rejected, then you go back to the drawing board and either revise your hypothesis or try to come up with a new one. And one of the things I was talking about at the very end is a lot of the controversy that you hear about what to do about COVID. Do the masks work? Do they not work? Should we wash our hands? Should we not wash our hands? I'll admit that a fair amount of that has been ginned up for assorted political reasons, but if you strip that away, a lot of that is due to the fact that, when a new virus shows up, we don't know, we've never seen this before. So scientists around the world have been testing hypotheses, and sometimes hypotheses that looked good at the beginning of the pandemic have turned out not to be so good. So I see people on Facebook complaining about how the CDC is changing its mind all the time. Or, Fauci doesn't know what he's doing because one week he says this, the next week that he says this. What's going on is basically science working the way it's supposed to.
It's really over.
Okay, sorry, somebody was talking just now. Okay, if you don't need to get my immediate attention, you're probably going to want to mute. Okay, cool. Oh, and I've got somebody to admit. Right. So ultimately, that's just how the process works. Those of you that follow nutrition may have encountered the same thing. It seems like one year, everybody's telling you to, athletes, when I was a kid, everybody was told to load up on carbs before a game. And now they're saying carbs are bad for you and you emphasize protein. And when I was a kid, cholesterol was evil. And now they're saying there's good cholesterol and there's bad cholesterol and your LDLs are dead. To the extent that's not people trying to market you dodgy supplements, that's ultimately science working the way it should. We test hypotheses. Sometimes one that looked valid turns out not to be supported. And then we toss it and keep on going. And it gets confusing for people who consume science as part of, recommendations for what to do with their lives, because sometimes the hypothesis is wrong. Sometimes a hypothesis looked good, but turns out not to hold up under repeated testing. And it's annoying, but It's the process working the way it should. If you have a hypothesis or a group of hypotheses that's been tested over and over and over and confirmed every time, and one that applies to a wide range of situations, we call it a theory. You might have heard of the germ theory of disease, Newton's theory of gravity, Darwin's theory of evolution, I don't know, Linus Pauling's theory of the chemical bond, and so on. Theory gets used a lot, and people use the term theory in everyday speech to mean random idea that I just pulled out of my bohonkus, and mean wild ass guess. I have a theory that I can transplant the brain of the human into the head of the zombie crocodile. No. Theories are very well tested. Theories are considered to be very reliable, but you never get absolute and utter proof in science. We are not going up onto Mount Sinai and coming down with tablets of ultimate truth. The reason is that any test of a hypothesis you could come up with is limited in space and time. Our labs are all on Earth. There's lots of hypotheses that are difficult or impossible to test anywhere else. And it's always possible that some, hypothesis that works very well and seems to be confirmed might be different if you tested it in another part of the universe or at a different time. Any test is limited by, the space you've got and the materials that you've got. But any theory that's interesting should predict things that will happen outside of your test. And every so often, even a very well understood theory collapses. You get pretty darn good reliability, but every so often, something that even people had a great deal of confidence in turns out not to work out so well. And that's just the way it goes. So yes, a common error is to assume that theory means assumption that some dweeb in a white lab coat pulled out of thin air. I don't know, dweeb is kind of a 90s word. I don't know what your generation would use for idiot. I don't know, geek. You know what I mean? And so every so often you'll hear somebody saying that such and such is only a theory. That doesn't mean it's only a guess. Theories work very well in the real world and have been tested repeatedly. But every now and then, not very often, but every now and then, even a well-tested theory gets shaken up. And I'll show you one. When I was your age, back when hair metal was still cool, back when Guns N' Roses and MC Hammer ruled the charts, would have been interesting if they'd collaborated. Sweet Child of Mine can't touch this. Anyway, when I was your age, you young post-millennials, get off my lawn, it was pretty standard knowledge that after infancy, after you're about 9 months to a year, the brain quits adding new brain cells. That's a picture of some brain cells. And you could lose brain cells. My roommate freshman year rushed Pi Kappa Alpha and came home drunk off his gourd every night for 3 weeks singing raunchy pledge songs. And I'm sure he lost an awful lot of brain cells, which didn't stop him from becoming an investment banker, making more money in a year than I'll see in 5 lifetimes, the jerk. Anyway, you could lose brain cells to injury or trauma. And there were ways that you could compensate for the loss. We were just learning at the time that brain cells can rewire themselves to an extent, meaning some recovery is possible from things like traumatic brain injury, but you could never grow new nerve cells in the brain. There have been multiple studies that show that's not entirely true, but I'll focus on a study of taxi drivers in the city of London, England. There's a small close-up of London. London's huge. London, the center of London is about 6 miles by 6 miles, which works out to be roughly 10 by 10 kilometers. And within that area, you have 25,000 streets. A lot of cities have their streets laid out on a rectangular grid, and that makes it fairly easy to navigate. So if you've ever been to New York, or especially Salt Lake City, which is like driving on a damn chessboard, it's pretty easy to find your way around. London is not like that. You can see that, you know, most of the streets, many of them don't make right angles. They're not laid out on a grid. From the air, it looks like a big plate of spaghetti. Many of the streets are one way, and of course, there's always road constructions and accidents and things like that. And there's thousands of places where people might want to go, thousands of landmarks, thousands of major buildings. And even Google Maps does not always get this right. To this day, if you want to be a licensed cab driver in London, you have to build this mental map of the entire city. You have to know 36 square miles with 25,000 streets running in every direction. And you have to know that like you'd know your living room furniture. And you have to take a test to get a cab driver's license, and nobody passes it the first time. I think the average number of times you have to take the test in order to pass it works out to be something like, I want to say 17. That usually takes 3 to 4 years of study. You've got to build, you know, Google Maps for a major city in your head. There's a part of the brain buried pretty deeply in it. It happens to be called the hippocampus. If anybody is curious, hippocampus is the Latin word for a seahorse. And the hippocampus in your brain looks a tiny bit like a seahorse if you dissect somebody's brain. And the hippocampus was already known to be involved in forming memory. We knew this by observation because patients who had had damage to the hippocampus from stroke or disease or brain injury of various kinds lost the ability to form long-term memories. They were permanently stuck in the present. Kind of an interesting case there. You'll hear about patients with this. Any of you psych majors will hear about patient MH at some point in your training. Anyway, so we already knew from observations that the hippocampus was involved in long-term memory. Well, they scanned a bunch of people's brains, and it turned out the hippocampus was larger in qualified London cabbies than in people who dropped out of the training or in people who had never been cab drivers at all. These are scans of the brain, and let me see. Yeah, right there. I'm kind of circling it, but inside these circles I'm drawing, you see there is a little red, tiny red circle. That's the location of the hippocampus. And with scans of the brain, it was possible to measure the volume of the hippocampus. So you can measure the size of.
Me neither, honestly, not gonna lie.
Nathan, is that you? Are you there? Okay, sorry about that. If you need to get my attention, you can unmute. But if you don't need my attention immediately, it's better to put things in the chat. Right. So what people did, what researchers did was scan the brains of people that were training to be cab drivers And they scanned them before the training and after the training. And that's what you're seeing over here. This gray bar right there, that is a measurement of the size of the hippocampus before they started training. This little thing that looks like the letter I is called an error bar. It's an estimate of inaccuracy in your measurements, and you'll encounter this in lab later when we talk about the idea of measurement error. But anyway, that bar shows the size of the hippocampus before they started. And next to it, that bar shows the size of the hippocampus when they'd completed. And you can see the size has gone up a great deal, probably about as much as 30%. If you compare the brains of cab drivers with the brains of people who dropped out, that's these non-qualified trainees over here, you can see there was no difference in size between beginning and the end of the training. And then these people here that are labeled controls, those represent people who never trained as London cab drivers. You know, these represent, I mean, I'm sure they were volunteers recruited for the study, but they had nothing to do with driving a cab. And as you can see there was no change in the size of the hippocampus over the same time interval as hippocampus size was measured for the cab drivers. So hippocampus size gets bigger in successful cab drivers, not in the washouts and not in non-cab drivers. And again, this was measured with brain scans. Nobody's head got cut open here. It's neat that we can do experiments like this non-invasively. So there's some further studies done in both humans and animals. And they've confirmed that the brain can rewire and remodel itself. And some parts of the brain, not all, have the ability to add new cells throughout life. That's really cool, because that could lead someday to better treatments for stroke or head injury. It would be really, really nice if if a part of your brain was damaged, it would be really cool if you could grow a new one. Maybe someday you will live to see that possibility come to pass. You never know. So what I learned when I was a student, much like you, gathering in the lecture halls of, it was called Percival Stern Hall back when I was a kid, something that I learned has turned out to be not entirely true. A theory that was wrong about something has been replaced by something that's more accurate. The work is still not finished. There's certainly lots more to be done. Why is it only some parts of the brain show this, but not others? The nerve cells that make up the new nerve cells come from a population of cells in your brain called stem cells. You might have heard about those because there's a lot of therapies that are being developed using stem cells. Are we going to be able to adapt these for the brain? I don't know. Might be worth trying someday. Bio majors, if any of you want to major in biology, our brain guy, well, our two brain specialists are Dr. Puri and Dr. Padberg. And if you take classes with them, they could maybe lead you to more. There's always more to learn and always more work to do. So science does not get it right the first time. And scientists are people. We're not, Anthony Fauci is a person. He is a human being. He is neither, a knowledge god or Satan incarnate. He's very good, but the scientific community has had its share of idiots and bigots, close-minded, arrogant twits, complete and utter babbling weirdos, and even now and again, frauds and crooks. I could name names. I have met people like this. we are not the communion of saints here. And even very good scientists make mistakes. We test hypotheses and they turn out to be complete duds. We test hypotheses and they look good, but we don't think to test them in a particular way. We test them and sometimes our test messes up. Sometimes the equipment doesn't work, or, the experiment is not well designed. We're people. We're imperfect. If science has anything going for it, it's not that it gives you truth, it's that it's self-correcting. Hypotheses that don't work ultimately get either modified or torn down. Part of the reason why science classes require new textbooks and new editions of textbooks on a regular basis, part of that is the publisher's greed, but another part of it is the fact that we do have to keep revising them. We keep finding new things. Mistakes and even frauds can last a while, but eventually somebody questions them and they get dropped and we keep on going. And that's the way it goes. And the greatness of science is not that it gives you truth. The greatness is that it fixes its own errors. There was a Danish guy that wrote a little poem that went like this: the road to wisdom, well, it's plain and simple to express. Error and error and error again, but less and less and less. That's what we try to do. All right, I talked about ways of testing hypotheses. And I talked about how in some cases you do observations or you do modeling, but there's a way to test a hypothesis called, experiment. And experiments are not defined by the equipment that you use. People tend to think that doing an experiment involves, large amounts of very expensive gear and people running around in white lab coats saying stuff that nobody can understand. That is not what an experiment is. An experiment is this. Let's say I've got Dr. Wagner's miracle pills, and I want to test the hypothesis that taking certain pills cures COVID-19. Okay, great. So I've got these pills, and I make people with COVID-19 take the pills, and the people with COVID-19 get better. Okay, great, wonderful. At best, I've shown that my pills do not kill people, but it does not mean that the pills are doing any good, because most people do make a recovery from COVID-19. I mean, don't get me wrong, there are still lots of people that die from it and lots of people that are left with permanent disability, or at least long-term. We don't know if it's permanent yet, but most people that get it are going to make some sort of recovery, even if they take no medicine at all. I mean, they'll be miserable for weeks, but yeah, most people can get better from this. And the mistake that I would be making is called the post hoc fallacy. Post hoc is Latin for after this. And that's the assumption that if thing X happens and then thing Y happens, then X caused Y. Or in Latin, post hoc ergo propter hoc means after this, therefore because of this. And that's an error, that's a mistake. Now, there are lots of times when you can say that, X happened, then Y happened, and X caused Y. If you take your eyes off the road and your hands off the steering wheel to answer a cell phone call, and then your car goes off the road and wraps itself around a telephone pole, then X did cause Y. That the cause of you wrapping your car around a telephone pole was you taking your hands off the wheel and your eyes off the road because you're taking a call or playing Angry Birds or whatever it is you do. Sometimes if X happens and then Y happens, X does cause Y, but you can't always assume that it will work that way. Two things can happen together, but that's no proof that one of them caused the other. As we say, correlation is not causality. Two things going together doesn't mean that one is the cause of the other. Good experiments will let you really test whether X really does cause Y rather than assuming it. I'll show you what I mean. 538.com, well, 538's a reference to the number of people in the electoral college, and they do a lot of discussions of political polling, but they do other types of statistical discussions as well. Now, it's a pretty good set of blogs, and the folks at 538.com analyzed large amounts of survey data, and they found out that there is a positive correlation between drinking coffee and cat ownership. If you drink coffee, you are more likely to own a cat. They found that eating bananas was correlated with higher scores on the SAT verbal part. They found eating potato chips correlated with higher math scores on the SAT. They found that eating egg rolls correlated with owning a dog. If you eat egg rolls, you are more likely to own a dog. And eating cabbage correlates with having an innie, a navel that points inward rather than sticking outward. And here's the thing, if you ask enough questions like this, you can always find some kind of correlation just by chance. The problem with them is that they don't mean anything. You know, drinking coffee might correlate with cat ownership, but that does not mean that drinking coffee causes you to own a cat, or that owning a cat causes you to drink coffee. Now, I don't know, as somebody who's got 6 cats in the house right now, I can say that owning 6 cats does cause you to drink alcohol. So there we would have causality there, but certainly not coffee. You know, I can't think of any way that eating cabbage would cause your navel to point inward, or vice versa, that having a navel that points inward makes you more likely to eat cabbage. So a lot of these correlations, there isn't any causality at all. They're just there. Okay, here's a fun one. 1954, a guy named Frederick Wortham published a book called The Seduction of the Innocent. This was one of the first of what people call a moral panic. Back when I was your age, the big moral panic was about satanic messages in heavy metal music and Satanism being present in role-playing games, Dungeons and Dragons. You know, everybody knew that KISS stood for, you know, Knights in Satan's Service. These days, the current moral panic is that liberal pedophiles are draining your children's blood in rituals in a pizza parlor basement that doesn't have a basement. You know this kind of thing. They pop up all the time. One of the first was this book that argued that American children were being corrupted by comic books. To be fair, comic books could be pretty violent and gory back in the day. That's one from 1953 that is, you know, pretty awful. I have no idea where Wortham got this idea, but he did claim that Batman and Robin were gay, and corrupting the minds of the youth of today, who would be, you know, seduced into a deviant lifestyle by trying to be like Bruce Wayne and Dick Grayson. Anyway, I bring this up because he claimed that 90% of kids in reform school were reading violent comic books. See the problem. 90% of kids in reform school were reading violent comic books. That's a correlation. 90% of kids who had been sent to reform school for being violent were reading violent comic books. The problem is that is no proof at all that the comic books were what turned the kids violent, right? It is possible that kids were turned violent by reading violent comic books. It's also possible that kids were already violent for some other reason, and that made them enjoy violent comic books. It's also possible that both being violent and reading violent comic books were caused by some third factor. Maybe kids that grow up really poor, maybe it's poverty. Poor kids turn to a life of crime, and poor kids buy comic books because they can't afford deluxe hardcover editions of classic literature. Or maybe it's a coincidence, right? Maybe there's something about comic books that makes kids turn violent. Or maybe kids that are already violent are more likely to read comic books. Or maybe being a criminal and reading comic books are caused by some third factor. Or maybe it's just one of those random things that has no more meaning than the fact that there's a correlation between eating cabbage and having an innie navel. Without more information, you cannot jump to a conclusion like that. You know, you can't assume without further work, without further study and better evidence that there is causation going on here. You can't assume that reading comic books causes violence or deviant behavior. And thinking about muscular superheroes in tanning beds in the nude, right? More serious note, you've heard about anti-vaxxers, of course. They tend to be in the news quite a lot. And of course, that didn't start with the COVID vaccines. Anti-vaxxers actually goes back all the way to the 1700s. There have been anti-vaxxers for as long as there have been vaccines. But in the 90s, the claim started being made, maybe it was in the thousands, maybe it wasn't quite that far back, but the claim was made mostly by a British doctor named Andrew Wakefield that childhood vaccines caused autism. And if your kid got vaccinated as a small child, your kid was going to grow up to be Dustin Hoffman in Rain Man. Here's the thing. There are parents who have had their kids vaccinated and then seen their children develop signs of autism. Why is that? Kids who have autism tend to start showing symptoms between about 12 and 18 months. Most childhood vaccines are given when a child is between 12 and 18 months. Yeah, you don't vaccinate newborns, but you do vaccinate them as soon as it's safe, and they'll start getting their first shots, between about 12 and 18. The two often happen at the same time. And so some parents have concluded that vaccines were the cause, that because they got their shots and started showing autistic symptoms, that the shots caused the autistic symptoms. Without further study, we cannot assume that this is true. Just because two things go together does not mean that one is the cause of the other. When the COVID vaccine first started getting given out back in January of this year, some of the first people to get it were the elderly. And I saw people freaking out because there were hundreds of elderly people who'd gotten the COVID vaccine and then died. Okay, that's tragic, but that does not mean the vaccine was the cause of the death. Elderly people die. They do it, it's what happens to them. They can die of lots of things. Elderly people are usually in pretty fragile health from the beginning. They're likely to have health problems, as a consequence of being old. And so it's not surprising that I don't know what lots is. It might have just been dozens. But it's not surprising that a certain number of the elderly got the COVID shot and then died. There's correlation there, but by itself, we can't assume that the shot was the cause of death. I should mention there was a recent long-term study in the country of Denmark that looked at hundreds of thousands of kids that followed up on the effect of vaccines and found out that ultimately vaccines could not be shown to cause autism. The rate of autism in the vaccinated population was not greater than the rate of vaccination or the rate of autism in the unvaccinated population. So I did not want to leave you hanging there, but the latest is that that correlation between vaccination and autism is not a causality. Vaccines are not the cause. Okay. Standing off the soapbox right there, there's lots of different factors that could influence something you observe, and we call these variables. So let's say I've got a COVID treatment and I'm testing it on a bunch of patients. Well, what are some factors that influence how well a patient does if he or she has COVID? Well, one could be age. You know, COVID, at least at the beginning, was much more deadly to the elderly than to the young, although that has changed now that the Delta variant has shown up. There could be other medical conditions. If you've already got conditions that suppress your immune system, if you've already got lung damage or lung disease, those can increase your odds of dying of COVID. Family genetics might well have something to do with it. I'm not sure if there's evidence for it, but some families might be better able to resist than others. Your level of access to medical care might influence how likely you are to survive. And that's tied to income and social class and all those things. Maybe there's lifestyle that has an effect. All of these could have some influence on the outcome of your COVID infection, whether you completely recover or recover but with lasting damage or don't recover. All of these could influence a given patient's outcome. If you're designing an experiment well, you isolate only one of those variables, and we call that the independent variable. And you design your experiment so that it looks for the effect of the independent variable on the thing that you're observing, which is the dependent variable. Think back to that experiment I talked about earlier with the cab drivers in London. You know, they scanned the brains and followed the careers of lots of people, cab drivers and washouts and non-cab drivers, right? They looked at a lot of people. There's lots of things that could have made those people different from each other. I'm sure those people were, of different ages, probably different sexes, probably different races. London is very multicultural. Probably different, states of health, probably different, different genetic backgrounds. Maybe some of those people came from really smart families and others didn't, for all I know. There were lots of things that might be different about all those cab drivers. What they did was isolate only one thing, and that is whether that person successfully completed driving, getting a cab driver's license or not. That's the independent variable. And then what they measured was they observed the dependent variable was size of the hippocampus. So all of that diversity of people got boiled down to two things. The independent variable was, do they have cab driver's licenses or not? And the dependent variable was, how big is that part of the brain. So I'll step away from COVID and let's look at some pretty flowers. This is actually some prairie in Arkansas, by the way. I'm seeing some Queen Anne's lace and some yellow coneflower and some purple coneflower. The UCA Nature Reserve looked kind of like this in July. What I want you to see right now is there's lots of plants and they're all different. We have different species of plants, you know, yellow coneflower, purple coneflower, Queen Anne's lace, handsome hairy, snake root, lots of different kinds of flowers. The plants are all different sizes and shapes. They get different amounts of light. You know, some are maybe in shade by the others. That's the thing about flowers. They look pretty, but they're always throwing shade. Right. Some of them might, you know, the soil might be a little patchy. So some of them might be in slightly richer patches of soil. Some of them might be getting slightly more water than others. All of those are variables. And if I wanted to go out and study the prairie, I might have to come up with a way to take many of those into account. This is an experiment where scientists are testing, I believe this is a new type of fertilizer. And you'll notice it looks different from the prairie. The ground's been divided up into these square plots, and plants are being planted in the plots. And if the scientists know what they're doing, each one of those plot has exactly the same type of soil, or as close as you can make it. You know, it may never be mathematically perfect, but as close as you can, you've got the same soil in these plots. Each of those plots is going to get the same amount of water, the same amount of light, the same amount of nutrients, and all of the plants in these plots are going to be the same species, right? Not purple coneflower and yellow coneflower and snake root and rattlesnake master and handsome Harry and mountain mint and all of the diversity of plants that you saw in the last picture. So all of these plants are going to be as much the same as we can manage. They're growing in the same conditions or as close to the same as we can practically get. And the only difference should be that some of these plots of plants are getting fertilizer and some of them aren't. So if we test the hypothesis that such and such fertilizer increases the growth of plants, we grow these identical plots of identical plants under identical conditions, except for the independent variable, which is going to be the amount of fertilizer that our plants are getting. Some of these plants will get lots, some might get a little, some will get none. That's our independent variable. And then what we measure is the dependent variable, which is going to be, you know, how large the plants grow. Maybe we will end up measuring their height, maybe uproot them and measure their weight. There's several ways we could measure that. But what we've done is we've isolated one variable that we're testing. That's the independent variable. That's the amount of fertilizer. And what we're measuring is the dependent variable. A good experiment, by the way, is going to use controls. And in the one we just talked about, some of these plots are going to get lots of fertilizer. Some might get a little bit. You know, there might be different levels of fertilizer that are made available. Some of those plots will not get any. They will just be left to grow naturally. So a control group is a part of an experiment where the variable being tested is left alone. And that's important because you have to compare the control group with the experimental group where you alter the independent variable. Let's say that I'm testing a medicine for COVID. What I would do instead of just giving it to all patients would be to divide patients up into groups. I would have to make those groups as much like each other as possible. It would not be fair to put all of the elderly patients into one group and all of the young patients into another. It would not be fair to put all the men into one group and all the women into the other group, because maybe men and women respond differently to my medicine. That sometimes happens. That's introducing an extra variable there. What I would want to do is, you could never make two groups of people exactly the same. They're always going to be different, but you can minimize all of your variables. So I might have groups of only, white men 25 to 34. Now, we would not want to restrict ourselves to testing our medicine on white men 25 to 34. Dr. Hill is our department head here. And one of the things that he's pointed out, he's a specialist on the heart and on how drugs affect the heart. And he's pointed out that a lot of heart drugs were tested only on men, and nobody got around to testing them on women. And there are subtle but possibly important ways in which hormones affect the way the heart responds to drugs. That's what he works on when he's not being the department head. So you would not want, if you're doing this right, to test your medicine only on men 25 to 34. You might want to do another experiment that recruits women. But let's say, for starters, you're testing it on white males 25 to 34. You divide that group up into an experimental group that gets the drug and a control group that doesn't get the drug. And you compare the outcomes between the group that got the drug and the group that didn't. And the group that did and the group that didn't should be as much like each other as possible, except for the fact that one got the drug and the other didn't. The independent variable in this case is, did you get the drug or not? The dependent variable is recovery rates from COVID. So if the drug works, then we might find that the people in the experimental group that got the drug recover, I don't know, maybe 5 days sooner than people who, on average, than people who didn't get the drug. That would be a best case scenario. On the other hand, we might find out that there's no difference between the experimental and the control group, and people who got the drug were just as likely to stay sick as people who didn't get the drug. In that case, we would have disproved our hypothesis. So good experiments always use control groups. By the way, this is not on the slides, but it's important. Good experiments always use as many observations as possible. One of the things that's going around is that a drug called ivermectin, which you can buy, you can buy it in Conway at the agricultural co-op, because it's used for treating horses and cows for intestinal parasites. You can use it on humans for treating intestinal parasites. If you ever get worms in your guts, ivermectin's pretty good. Shoot, the folks that discovered it won the Nobel Prize about 7 years ago. It's a good drug. There were some early tests that suggested that ivermectin would be effective in fighting COVID. The problem was they were all done on extremely small numbers of people. And like, if your experimental group and your control group both are 10 people, then there's a chance that any result that you do get is purely going to be due to random factors. It's not going to be because your drug really does treat COVID. The same was true for back about last year in March and April. People were taking this stuff called hydroxychloroquine, which is usually used for malaria. And there were some very early experiments that suggested that hydroxychloroquine might be good, might be effective in treating COVID. But there were problems in how the experiment was executed. The doctor that did the tests was kind of sketch. And what I remember is that the experiments that he did were based on very small numbers of patients. Once it was possible to test hydroxychloroquine on larger numbers of patients, the effect went away. So the alternative treatments that are getting, passed around my Facebook feed all the time have been tested. The problem is that further testing with larger numbers of patients turned out to show that they weren't effective. Ivermectin is very good for you if you've got intestinal roundworms. The latest is that it doesn't seem to be effective if you take it to ward off COVID. Okay, so what I've been talking about is the best known type of experiment called a clinical trial. You'd get as many people as you could. You divide them into two groups. One group would get a drug, or maybe one would get a vaccine. I just noticed this slide switch from drug trials to vaccine trials, but it works the same way. One group gets the vaccine, the other group doesn't. The independent variable is whether or not people get the vaccine. The dependent variable is how often people in both groups get COVID. That says the flu, it should say COVID. So if the people who get the vaccine get fewer cases of COVID on average than the people that don't, we would have confirmed the hypothesis. And in labs, you'll get a sense of how we can use the methods of statistics to determine whether or not a difference between groups is significant. We can measure how fewer have to be for us to accept the hypothesis that our vaccine works. And again, we'd have to match the experimental and control groups as closely as possible, same ages, genders, and races. Now, we would actually probably want to repeat our experiments on several different groups. You'd want to make sure that a drug or a vaccine doesn't work one way in men and another way in women, or one way among people of European descent and another of people from African descent. So you would want to test it on a wide range of people. And as I mentioned, one of the things Dr. Hill has noted is that heart drugs have sometimes been tested only on men, and there isn't good data on whether they work as well in women. Male and female hearts are subtly different from each other because they're exposed to different types of hormone. And that's what he works on. So yeah, in a real trial, you would want to test this on a wide range of groups, but in any given trial, you need to match the groups as closely as you can. You can never eliminate all the variables, but you can minimize them. So that, by the way, is actual data from the 2020 trial of the AstraZeneca vaccine in the UK. What you're looking at is the cumulative number of trial participants who test positive for COVID. That men ACWY, don't worry about what that stands for. I don't even remember, but that is the control group. So they took a group of people, gave them the control, and the rate of COVID cases went up like this. In red, you've got the people who got the AstraZeneca vaccine, which at the time was called ChAdOx1. And they gave those people the vaccine and then observed them over time. And you can see that the cumulative rate of COVID cases was significantly lower. In the unvaccinated group, they got up to about 4% coming down with COVID. In the vaccinated group, it was less than 1%. That's a big difference. So that's some actual data showing you, the difference between the experimental group in red and the control group shown in blue. So there you have it. There's actual data from the trial of the Pfizer vaccine. People on my Facebook feed keep complaining that this vaccine has not been properly tested. The fact is they tested it on over 43,000 people. That's about how big Conway was about 15, 20 years ago. That's a fair number of people. Blue here shows the cumulative number of people who did not get the vaccine and tested positive. From dose one, it ended up with, again, about 2% of that control group testing positive for COVID. The experimental group, once the immunity kicked in at about day 10, they didn't even crack 0.4%. Maybe 1/3% of the experimental group tested positive for COVID. So that's the difference between an experimental group and a control. The control group, went up like that. The experimental group stayed way the heck down. But if all we had done is given people the shot, they might have a low rate of getting COVID, but we wouldn't have anything to compare that rate to. So that's what you need the control for. You need that to give you a basis for comparing the results that you see in your experimental group. One thing you have to watch out for in drug trials is something called the placebo effect. This was first noticed in World War II. It was, I think, it was an army medic who was treating wounded American soldiers, and he ran out of morphine. That's a painkiller. And when he ran out of that stuff and he had patients, screaming, out of desperation, thinking it might do some good, he started giving his wounded patients injections of plain water. To his astonishment, what he found was that the patients who'd gotten the water injections actually felt pain relief. They were helped as much as the ones who'd gotten morphine. And the reason is that one of the biggest variables when you're talking about treating people is the mind. These wounded soldiers were given a shot by somebody that they trusted, and they felt less pain because they expected they would feel less pain. That's called the placebo effect. Placebo, I will never ask you what Latin words mean on a test, but some people find that it's helpful in learning vocabulary. Placebo is Latin for I am pleasing. I please. And a placebo is a substance that is useless, like water or, sugar pills or something like that. But because patients are getting it from a trusted source, it makes them feel better. So in a clinical trial, the control group is not just left alone. We would not test a vaccine by giving the experimental group the vaccine and not giving the control group anything. The control group would get an injection of plain water or mild salt solution or something like that. And they would be given it by the same people that are giving the experimental group that shot. And it would be done in such a way that neither the people giving the shot nor the people in the experiment knew whether they were getting the vaccine or the salt water. An experiment set up that way is called a double-blind experiment. So if you're in an experiment like that, you would get an injection. It would look just like the real vaccine, but you would not know, and neither would the nurse giving the shot, whether that was the real vaccine or not. That avoids the placebo effect Well, it doesn't avoid it, but everybody who gets the shot from a trusted nurse, might feel the placebo effect, but the placebo effect is not going to be a confounding variable. Am I remotely making sense? Sorry, I heard somebody laugh. All right, I'll let that go for, well, oh, wow, something in the chat. Okay, I seem to be, yes, I am making sense. Cool. That's always a good thing. So yeah, scientists are human. We're not free from preconceived notions and prejudices. I've got them, you've got them, everybody's got them. Scientists also tend to be people that really love ideas, and we tend to get attached to them. And I said this earlier, but hypotheses are creative acts. Coming up with a good hypothesis is as tough as coming up with a catchy tune. And if you come up, if you write a song, you really, really, really want people to love that song. And, maybe you hope it's going to be a hit and get on the charts and make you lots of money or something like that, because that would be really cool. Science is the same thing. We love our hypotheses. We really, really would love it if they were true. And we know this. If you're a good scientist, you know this in advance, and you try to build experiments that work against the way your own brain does. You try to build experiments in such a way that you eliminate as much of your own bias as possible. That's what makes this difficult to do. It's so easy to conclude that your hypothesis works and your experiment has confirmed it, and this is great and this is awesome, and the Nobel Prizes are going to start rolling in any day now. It's very easy to love your ideas too much, and a good experiment bulletproofs you against falling in love too much with your own ideas. Okay, I probably don't. Okay, I'll start with this on Thursday. We don't really have time to get into this, although I do think it's important, because one hypothesis in the 19th century that was very popular was the hypothesis that Africans and African Americans were mentally inferior to people of European descent. There were scientists in the 19th century that wrote big books proving this, giving lots of data, lots of facts. And we need to look at, I use this as an example of how bias can be built into the practice of science if you are not very, very careful about it. There is no support for the idea that people from one continent are mentally inferior to people of another. That's bullshit. But that was widely believed in the 19th century, and I'll use that as an example for how we tried to design experiments to avoid our own biases, because that's something important I think people ought to know. But I am out of time. So by the power vested in me by the state of Arkansas, I will stop recording.